Fine. So let's get along with the proof of Montel's theorem. See, so the key point that you have to remember is that the difference between Montel's theorem and the Arzela-Ascoli theorem is that the Arzela-Ascoli theorem is for continuous functions, okay, defined on a compact matrix space, right. Continuous functions, of course, real valued or complex valued. In fact, you can even have continuous functions with values in a compact matrix space, okay. Whereas the Montel's theorem is for, of course, it's for analytic functions, and then we are going to extend it to meromorphic functions, and these are going to be defined on domains, okay, which are certainly not compact, right. So, one thing that you have to contrast and compare is that the Arzela-Ascoli theorem, as it is for continuous functions defined on compact metric space, whereas the Montel theorem is for analytic functions and later on for meromorphic functions defined on a domain, okay. So it's not a compact set, right, it's an open connected set. Then that's one difference. That's actually two differences. The domains are different. In the Arzela-Ascoli theorem, the domain is a compact metric space. In the Montel theorem, the domain is the domain of the function is actually a domain in the complex plane, right. Then the second thing is, in the Arzela-Ascoli theorem, we are worried about real or complex valued continuous functions, whereas in the Montel theorem, you are worried about analytic functions and later on meromorphic functions, okay. Then the other important thing is that what is the similarity? The similarity is that both of these theorems tell you when a family of functions is compact, okay. Now if you look at it from the viewpoint of the Arzela-Ascoli theorem, compactness it corresponds to sequential compactness, okay, and sequential compactness is just the condition that given a sequence of functions in the family, you are able to extract a convergent subsequence, okay. And whereas in the Montel theorem, what will happen is that you will have a normal version of this. So the Montel theorem will tell you that you are given family of functions is compact in the following sense, that given a sequence in the family, you can extract a subsequence, but now this subsequent is not convergent in the sense of functions, that is, it's not uniformly convergent on your domain, but it is uniformly convergent only when restricted to compact subsets of the domain, that is normal convergence, okay. So that is the difference. In the Arzela-Ascoli theorem, what you get is convergence with respect to uniform convergence, okay, and that means it's uniform convergence on the whole space, whereas in the context of the Montel theorem, what you will get is convergence with respect to only compact subsets, that is normal convergence, okay. So that is the subtle difference that you have to understand, and but the punch line is that in the Arzela-Ascoli theorem, you need, for this compactness or sequential compactness, you need the two properties of the for these functions in the family to satisfy. One is uniform boundedness, okay. The other one is equicontinuity, all right. But this is for continuous functions in the Arzela-Ascoli theorem case. But if you come to the Montel case, okay, equicontinuity is free. It comes because you are looking at analytic functions. Because you are looking at analytic functions, you know that the derivatives of the functions are the derivatives are expressible using the Cauchy integral formula, and then you can estimate the integrals, and therefore you get the so-called Cauchy estimates, and the Cauchy estimates will tell you automatically that the derivatives are bounded, and it's a natural fact that whenever the derivatives are bounded, the original functions are themselves equicontinuous. So equicontinuity comes for free, it comes automatically for if you are looking at analytic functions. But if you are looking at that is in the context of Montel's theorem. But if you are looking at the context of the Arzela-Ascoli theorem, you have to give equicontinuity as an extra condition, because all you have is continuity to begin with of the functions. Okay, so so I was so the first point I want to show is that this family, I am starting with the domain D in the complex plane, and script f is a family of analytic functions on D, and it's normally uniformly bounded. So it's uniformly bounded when restricted to any compact subset of D, and I have to show that given a sequence in the family, I must be able to get a subsequence that converges uniformly on compact subsets. Okay, and the first thing I will show is that equicontinuity is automatic. Okay, so so for that, pick a point Z not belonging to D. Okay, choose rho greater than 0, so that the closed disk centered at Z naught radius rho, the set of all points in that closed disk is inside D. Okay, you can do this because D is an open set. Of course, I am working with a non-empty open set. Okay, so D is an open connected set. So you give me a point of D, by openness there is always a small disk surrounding that point which is also in D, and I can take a smaller disk along with the boundary inside that disk. Okay, so I can find this rho. Alright. Of course, you know the reason why I am including the boundary is because I want a compact set. Okay, if you take a closed disk, it's both closed and bounded, so it's compact, and then I can use the hypothesis that the family of functions is then uniformly bounded on this compact set. Okay, so let M be a uniform bound for all. Let M be a uniform bound for all f belonging to script f inside mod z minus z naught less than or equal to rho. Okay. So what does this mean? This means that mod f of z is less than or equal to m for all f in script f, and for all z with mod z minus z naught less than or equal to rho. Okay, and now what I would like to show is that I would like to show that in a smaller disk, what happens is if you take a smaller closed disk, then the family is actually equicontinuous. So what I do is I choose a smaller closed disk. So basically, you know, if I draw a diagram, so it's going to be like this. I'm going to have this. I'm going to have this disk centered at z naught. Radius rho, and then you know now what you do is choose a rho 1 which is less than rho, a rho 1 which is positive and less than rho. Okay, so that I can consider the smaller closed disk of radius rho 1 centered at z naught. Okay, and look at z in mod z minus z naught less than or equal to rho 1. Okay, so the situation is like this. I take a smaller disk, and this length is rho 1. Okay, I'm looking at this smaller disk. All right. Now for z prime in this smaller closed disk, by the Cauchy integral formula, well, if you want second Cauchy integral formula, what do you have? You have, if I write it out, I will get mod, well, first let me write out the formula without worrying about the estimating it. So f dash of z prime is 1 by 2 pi I integral over mod z minus z naught is equal to rho f of z dz by z minus z prime the whole squared. So this is the Cauchy integral formula. Okay, and mind you, the contour of integration is this outer circle taken with the positive sense, right? And now the point is that you have this, but then I want to basically what I am trying to show is that I am trying to show that in the smaller closed disk all the derivatives are bounded, okay, and because all those derivatives are bounded in the smaller closed disk, the family is equicontinuous. Okay, so all I am saying is that pick any point, there is a small closed disk around that point where the family is equicontinuous, and since the point that you picked was arbitrary, this will tell you that the family is equicontinuous on all of D. Okay, so you get equicontinuity for free. Okay, and of course the reason is because you have the Cauchy integral formula. Okay, so what is this? The modulus of this will be modulus of this, and you know the modulus of the integral is less than or equal to the integral of the modulus. It's less than or equal to the maximum of the modulus of the integrand as the argument variable of integration varies over the region of integration multiplied by the length of the contour. So what I am going to get is I am going to get this is less than or equal to 1 by 2 pi. That is what I will get for this term outside, 1 by 2 pi I, and the length of this contour is going to be 2 pi rho. It is just a circle radius rho, alright. And then what about the integrand? The modulus mod f is going to be bounded by m, because mod f is always bounded by m for all f in the family script f. Okay, so mod f is going to be bounded by m, so I can put this m here. And as far as the denominator is concerned, you see, look at this. See, the z is lying on the contour of integration. Okay, and I'm my z prime is, see, my z prime is lying in the smaller disk, so my z prime is here. Okay, and the distance between z and z prime is therefore at least rho minus rho 1. Okay, so mod z minus z prime is greater than or equal to rho minus rho 1 for mod z minus z naught is equal to rho. Okay, if you take z on the outer circle, then the distance from a point to the inner circle has to be at least rho minus rho 1, which is the difference of the radii. Okay, the closest z prime can get to z is along this radial line from z naught to z, and that closest distance is rho minus rho 1. Okay, so you know why I need this inequality, because now I want to I have to invert the inequality. And then the direction of the inequality will change. So I will get 1 by mod z minus z prime the whole squared mod will be less than or equal to 1 by rho minus rho 1 the whole squared. So I can put a rho minus rho 1 the whole squared here. Okay, so finally I will end up with just m rho by rho minus rho 1 the whole squared. Okay, and this is a bound. So this is true. This is true for all functions f in script f, and for all z prime with lying in the inner disk mod z prime minus z naught less than or equal to rho 1. Okay, so this happens. So in sum what have we shown? We have just shown that the modulus of the derivatives of all your functions inside in a smaller closed disk, they are all uniformly bounded by this constant. Okay, and this constant has got nothing to do with any particular point. See, this constant that I have got on the right side is m rho by rho minus rho 1 the whole squared. That has got nothing to do with the point z prime, except that the z prime should lie inside this smaller disk, and it has got nothing to do with also the function f that I chose from the family. So it's a uniform constant. Okay, so what you have shown is that the because of analyticity, the functions, the derivatives are bounded. Now because the derivatives are bounded, you get equicontinuity. And how is that? You get that by actually integrating these functions. Well, you know, if I had taken so for if I take 2 points z1 and z2 with mod z1 mod zi minus z0 less than or equal to rho 1, that is if you take 2 points in this smaller closed disk. Okay, you take 2 points z1 and z2 in this smaller closed disk, then if you fz1 minus fz2 is nothing but the result of integrating from z1 to z2 of f dash of z dz. Okay, this is because of this fundamental theorem of integral calculus. The moment the function has an antiderivative, then the integral is just the difference of evaluation of the function at the final and initial points. Okay, so you have this. but of course the path of integration here really does not matter so long as the path lies inside this closed disk, and it's well, you know, I am taking the path to be the straight line segment from Z1 to Z2. If I take that straight line segment path, then what will happen is that, well, if I put a mod to this, I will get this is less than or equal to mod f dash of z, okay, which is now I have got a bound for that, and mind you this z is lying on the path of integration, and therefore it is inside this smaller closed disk, so this bound applies. So I will get this m rho by rho minus rho 1 the whole squared, this is the bound for f dash of z, okay, and the length of this contour from Z1 to Z2 is just the length of the line segment from Z1 to Z2 that I am choosing, and so it will be a mod Z1 minus Z2. This is what I get. Okay, so now that's it. This gives me equicontinuity because for epsilon greater than 0, choose delta to be less than, you know what to do. You have to choose it to be less than rho minus rho 1 the whole squared by m rho times epsilon. You choose this, okay. Then mod Z1 minus Z2 less than delta will imply that mod FZ1 minus FZ2 will be less than, you look at this quantity, I have to replace this mod Z1 minus Z2 by the bigger quantity rho minus rho 1 the whole squared by m rho epsilon, okay, and I will get less than epsilon. Okay. So basically this is true for all Ez1 and Ez2 inside mod Z minus Z1, mod Z minus Z0 less than or equal to rho 1. Okay. So what you have shown is that given any 2 points, the moment 2 points inside the smaller closed disk are lesser than delta, the function values are lesser than epsilon, and this works for any 2 points and for any function. So you have shown a kind of you have shown a uniform equicontinuity of the family inside the smaller closed disk. Okay, so thus script f is equicontinuous inside mod z minus z0 in the smaller closed disk. Since z0 was arbitrary, f is equicontinuous on D. So I am writing EQCTS for equicontinuous on D. So this is the important point. I mean, this is the distinguishing feature between Montel's theorem and Arzela-Ascoli theorem in philosophy. While in the Arzela-Ascoli theorem you need equicontinuity, in the Montel theorem you get equicontinuity for free because you are already working with analytic functions, and so the moral of the story is, if you have a uniform bound for your functions, that gives rise to a uniform bound for the derivatives, okay, that is because of the Cauchy integral formula and estimation, and the uniform bound for the derivatives gives you equicontinuity for the original functions. So just the uniform boundedness of the original functions for analytic functions is enough to give you equicontinuity also, okay. So we are now in good shape. Now you see, now I can actually apply the Arzela-Ascoli theorem. For example, on this, if I take any, you take any compact subset of D, okay, take any compact subset of D, then these continuous functions will restrict to continuous functions on that compact set, of course. Okay, any continuous function on a topological space, if you restrict it to a subspace, it will remain continuous if you take for the subspace the subspace topology. Okay, so if you take a compact subset of the of D, if you restrict these this family of functions, you are going to get continuous complex valued functions on that compact set, and they are also going to be equicontinuous because we already checked equicontinuity. Alright. So and mind you, you all already assumed that the family is normally bounded, normally uniformly bounded. Therefore they are also going to be uniformly bounded on that compact set. Therefore the usual Arzela-Ascoli theorem applies, and given any sequence I can extract a subsequence. Okay. So I have brought myself into the purview of applying the usual Arzela-Ascoli theorem. Okay. So let me write that down. Thus for any compact set, for any compact subset K in D, the Arzela-Ascoli theorem applies to give a convergent subsequence for any given sequence in script f. Okay. So you are able to apply the Arzela-Ascoli theorem, but you are still, but we are still not. I must say we are only halfway through the Montel theorem. See, there is a small again there is a small subtlety that you have to notice. What have we achieved so far? Give me a compact set K. Suppose I start with a sequence in the family F. Give me a compact set K, I will be able to get a convergent subsequence. But you see, if I change the compact set, I may get a different convergent subsequence. Okay. Whereas what does the Montel theorem say? The Montel theorem says you start with a sequence, you can get a subsequence, the same subsequence which will work on every compact set. You see, that is the subtle difference. So we are halfway through. For given a sequence in F, in the family script F, you can always extract a subsequence which converges on that compact set. But if you change the compact set, the subsequence can change. What Montel theorem promises is one subsequence that will work for all compact sets. Okay, and the way to get that is it's a very clever thing. It's again a diagonalization argument. Okay, if you go back to the Arzela-Ascoli theorem, we use a diagonalization argument. Actually, in the proof of the Arzela-Ascoli theorem, one way where we tried to show that, you know, if a family is equicontinuous and uniformly bounded, then it is sequentially compact or compact. So what we did was we took a family of continuous functions in that family, and we tried to extract a convergent subsequence. But since we were in a closed subspace, we just contented ourselves with extracting a Cauchy subsequence. Okay, but the point is, how did you get this Cauchy subsequence? We knew that the metric space was on which the functions were defined was compact, so we knew it's separable. So we took a separable dense subset. We took a countable subset of points x1, x2, x3 and so on, which was dense, and then what we did was we took this sequence, first applied it to x1, okay, and by boundedness this gave you a subsequence of functions which converged at x1, and then we applied that subsequence of functions to x2, okay, and again being bounded we got a further subsequence which converged at x2, and then we did this process ad infinitum. Okay, we got a matrix of functions, and then we took the diagonal sequence, and that diagonal sequence was a sequence of functions that converged on this countable dense subset, and then we used equicontinuity to interpolate and to conclude that therefore this diagonal sequence converges on all of x and uniformly. Okay, that's so this is, you see, the same kind of diagonalization argument we'll use now. Okay, and and the key to that is a special construction. What you do is that you construct a sequence of increasing sequence of compact sets which fill out your domain D. Okay, so it's more like, you know, if your domain D, for example, is a whole complex plane. Okay, an increasing sequence of compact sets which fills out the complex plane will be just a sequence of disks, closed disks of increasing radii. Okay, so it's just that, but you'll have to take care about the boundary. Okay, so we'll do that. So let me write this down. Note that this convergent subsequence could change if K were changed, but Montel's theorem promises a single subsequence that converges uniformly on any compact subset. Okay, so that's the subtle difference. So what we will do is that, so I'm going to look at these sets Dn. So here is my set Dn. Here is how I define it. It is a set of all points in D with the following property: mod z is less than or equal to n. Okay, so it's a subset of the closed disk centered at the origin radius n. All right. So it's anyway this first condition tells you that each Dn is automatically bounded because there is a bound. All right, and here is the second condition, which is the distance from z to the boundary is at least 1 by n. Okay, so it's a rather it's a rather nice condition. Okay, so what I want you to note is that there are only essentially two cases you have to understand. See, if dou D is empty, what does it mean? If dou D is empty, it means D is the whole space. Okay, dou D can be empty only if and only if D is the whole space, because after all, dou D put together, dou D is the boundary of D. Dou D, and that's a closed set. If you take dou D and take the union with D, you get D closure. Okay, therefore dou D being empty is the same as D equal to D closure. But if D is equal to D closure, you are saying D is closed, but D is already open. D is both open and closed. Okay, and if it is non-empty, it has to be the whole space because the whole space is connected. Okay, so the situation that dou D is empty corresponds to D is the whole complex plane. Okay, that means actually you are looking at a family of entire functions. Okay, and in that case, this Dn is just the sequence of disks of increasing radius. Okay, and this condition will become useless. The distance between d, z and dou D is greater than or equal to 1 by n is superfluous. Okay, you write this condition only when it makes sense only when dou D is non-empty. Okay, if dou D is empty, if you want, define the distance to be infinity, so that infinity is always greater than or equal to 1 by n. Okay, if you want, but think of this condition only when dou D is non-empty. Okay, so what is it that you are doing? The reason why we put this condition is because you can't include everything in D. Okay, if you try to include everything in D, you will have issues if you try to because D is open. Okay, because D is open, basically I want all these Dn's to be compact. Okay, so the fact is that D is actually the union of all these Dn's. D is the union of all these Dn's. This is one. The second thing, or rather facts. The second thing is Dn is compact for each n. That is the second condition. And the third, this is the very important condition. Any compact subset is contained in some Dn. And any compact subset K of D is contained in some Dn. So this is the beauty about this collection Dn. And you see, it's this compactness that I am worried about. See, each Dn is automatically bounded. There is no problem about that. Each Dn is automatically bounded. So the only thing that prevents it from being compact is it not being closed. Okay, if you check that each Dn is also closed, then each Dn will become both closed and bounded, so it will become compact. Okay, now the big deal is it is for making sure that each Dn is closed that I have put this extra condition that D distance of z to dou D is greater than or equal to 1 by n. That's the reason I put. That's because you see, suppose my region is just unit disk. Suppose D is just the unit disk. Okay, suppose D is just set of all z such that mod z less than 1. Okay, then what is D1? D1 is D. What is D1? Is set of all points whose modulus is less than or equal to 1. Okay, that is if I forget the other condition. Okay, forget the second condition, that the distance from the point to the boundary of D is greater than or equal to 1 by n. Suppose I do not put that condition, and if D is the unit disk, then D1 is D. So D1 becomes the unit disk and it is not compact because it is not closed. Okay? So therefore, it is for the closedness of each Dn that you put this extra condition, the distance, you are throwing away part of the boundary. Okay, you are taking points from a certain particular distance 1 by n from that boundary, and you are not allowing points to go very close to the boundary. You allow up to a certain distance, minimum distance, which is 1 by n, and that condition makes each Dn closed. I mean, that is the significance of this condition that I have circled. Okay, so if you draw a diagram, you know, it's more like this. It's like you know, here. So let me draw somewhere here. So you know, suppose this is the plane, and suppose this is your domain D. All right, then you know what is D1? D1 is all those points which are lying in the. So let me draw this. This is too big. Let me get rid of this. Oops. So you know, so these are all the points in the unit circle. Okay, this is mod z less than or equal to 1, and so I'll also include the boundary because I have allowed less than or equal to 1. Okay, and then I am looking at all those points of D whose distance from I think I'll have to slightly modify this diagram so that I get a non-empty set. So let me draw something like this. Okay, so suppose this is my suppose this is my D. Okay, and mind you, D doesn't contain the boundary, so you know I should redraw this. I should draw it like this. So this is my dou D. This is the boundary of D. Okay, it's like a half plane except that the boundary is not a line, if you want. Okay, now what is D1? D1 is all those points lying in the closed unit disk, okay, whose distance from this boundary is at least 1. So if you actually calculate it, you see what you will get is you will get this. So with this distance 1, okay, this will be D1. This is what D1 will be. Okay, and this boundary is included. Okay, because these are the points whose distance from the boundary dou D is at least 1, and points less than with distance less than 1 are all not included. Okay, so this is D1. If next, you know, if you take D2, okay, then what will you get? So I have this disk. Now this is a bigger disk, radius 2. All right, and what am I going to get? I'm going to look at all those points inside this closed disk. Also for which the distance from the boundary is greater than or equal to half now. Okay, so what I'll get is I'll get this. So basically I'll get this. This region that I have shaded with vertical lines, that is going to be D2. Okay, so like this you can see that these, on the one hand, the DNs are becoming bigger and bigger so as to cover D. On the other hand, they are coming closer and closer to the boundary of D so that you don't lose any points very close to the boundary. Okay, this is what is happening. But but keeping all the Dn's away from the boundary by a distance of 1 by n is the condition to make them a closed subset, make each of these closed. Okay, so that is the reason each Dn is therefore closed and bounded. So each Dn is compact, and the union of all the Dn's is D. Okay, so you can make this, you can write out all the details basically using properties of basically using the fact that, you know, the distance function, the metric function is a continuous function. That's what you have to use if you write down everything in detail. Okay, the distance function is always a continuous function, so you have to use that. All right, and you can see several things. It's very clear that all the Dn's will cover D. Okay, because you give me any point of D. Okay, it has to lie in some big enough closed disk, some mod z less than or equal to n. Okay, and if the point is and it has to be at some distance away from the boundary, because D doesn't contain its boundary, it's an open set, so every point in D has to be away from the boundary. So you can always find every point of D in some Dn, okay. So the union of all the Dn's cover D, okay, and all the Dn's are compact. And what is more beautiful is you give me a compact subset of D. If you take a compact subset of D, such a compact subset will be in some Dn certainly, because it will be contained in some big enough closed disk, okay, and it will have, because it is compact, its distance from the boundary of D will be some finite quantity, okay. So it will be contained in Dn for n sufficiently large. So given any compact subset of D, it has to be contained in Dn for some sufficiently large n, okay. Therefore the beauty is that you have constructed this increasing sequence of compact subsets which cover the whole of D, and now comes the trick. What you do is, for each of these subsets you can apply the Arzela-Ascoli theorem, okay, and then use a diagonalization argument and pick out a diagonal subsequence which will now converge on all compact subsets of D, and that is the sequence that is promised by Montel's theorem. So that is what I am going to write down. So so let me write this down. Let's go. Okay, so let me write it here. So let f1, f2, etc. be a sequence in script f, and apply the Arzela-Ascoli theorem to extract a convergent subsequence on D1, okay. Mind you, D1 is a compact set, okay, it is a compact subset of D. So on D1 it is a compact subset, so it is a compact metric space, and therefore I can apply the Arzela-Ascoli theorem, and on D1 I can get a convergent subsequence by, and here when I say convergent subsequence, is uniformly convergent, okay, because it is convergence in the space of functions. So extract a so here let me put uniformly, okay. So call that subsequence as f11, f12, f13. Now you see that you are in the diagonalization business, okay. Now what will you do? Now you take this subsequence f11, f12, f13 and again apply the Arzela-Ascoli theorem to get another subsequence which will converge uniformly on D2, and call that as f21, f22, f23, okay, and proceed in this manner. And then you take the diagonal sequence will be a subsequence of the original sequence which will converge on all which will converge compactly, which will converge uniformly on all Dn's, and since any compact subset of D is contained in some Dn, therefore it will also converge uniformly on all compact subsets of D, and I am done, okay. So that is the trick. So let me write that down. Again apply the Arzela-Ascoli theorem to extract a subsequence f22, f21 that converges uniformly on D2, okay. Continue this way to get fn1, fn2 that converges uniformly on, I should say, D1, D2, etc. Dn. So in fact I should not put comma, I mean instead of putting comma I can actually put union, union di I equal to 1 to n, okay, and that is it. So we are in the following situation. So you have this original sequence f1, f2 and so on, then you have this f11, f12 and so on. This is subsequence, and the point is it converges uniformly on D1, and then you have f21, f22 and so on. This is also a subsequence, this that converges uniformly on D2 and D1. So that is D1 union D2, okay, and you go like this ad infinitum, you end up with f n1, f n2 that converges uniformly on union I equal to 1 to n di, okay. Then the subsequence, the diagonal subsequence. So this is a diagonal trick. The diagonal subsequence f11, f22, f33 converges uniformly on compact subsets of D. That finishes the proof of the. Of course, I must tell you that D1 union D2 is just D2, okay, because D2 is bigger than, and this union I equal to 1 to n di is just dn actually, okay. Each di includes the dj's for j less than I, because it is an increasing collection of compact sets, okay, and any compact subset of D is contained in one of the dj's, okay, and therefore this diagonal subsequence will converge uniformly on that compact set. So starting with a sequence of analytic functions defined on the domain D, okay, just putting the condition that this sequence is uniformly bounded on compact subsets of D, namely that it is normally uniformly bounded, just that condition is good enough to guarantee that you get compactness, in the sense that any sequence from this family will admit a convergent subsequence, and that is the point of Montel's theorem, okay. So what we will need to do is that we will have to, you see, somehow the derivatives are entering into the picture, and the trick is that you want to extend this to meromorphic functions, but you know, for meromorphic functions derivatives are not defined at the poles, but then we have replacement for that, we have the spherical derivatives. So the trick is that you try to get another version of this Montel theorem which will work for meromorphic functions, and you try to use a spherical derivative and still everything works, okay. So you get a Montel's theorem for meromorphic functions, okay, and that is what we are going to do next, because finally we have to worry about meromorphic functions for the proof of the Picard theorem.